Hi, I'm Howard, and this is how it works. Second video, after a mildly successful rollout of the first one, another video on electricity, but this time part of GCSE physics. This is usually covered at age 14 to 16 in the UK, though it does also apply to A-level as well, ages 16 to 18. This is IV characteristics. In this video, we'll talk through the circuits required to measure the IV characteristics of three different components, the graphs we get as a result of doing that, and why those components have those shaped graphs. The three components are the ohmic resistor or ohmic conductor, the filament lamp, and the diode. So for our first component, the ohmic resistor, we need a circuit to measure the current and voltage through the ohmic resistor. The circuit looks like this. In this circuit, we've got a power supply in series with an ammeter, our ohmic resistor, and a variable resistor, and a voltmeter in parallel with the ohmic resistor. This will measure the current through the resistor as well as the voltage across the resistor. The variable resistor is there to control the current in the circuit. After varying the current in our circuit and measuring the voltage at every variation of current, we'll get a table of results. We can then plot a graph of current against voltage, I against V, hence IV characteristic graph. It should look something like this, a straight line graph through the origin. The straight line graph shows us that I and V, or current and voltage, are proportional, and they should be, because an ohmic conductor, like this component, obeys Ohm's law. Ohm's law is V equals IR, or voltage equals current times resistance, showing us that voltage and current are indeed proportional. That is why an ohmic conductor has this characteristic IV graph. It's ohmic, it obeys Ohm's law, current and voltage are proportional. The gradient of this graph is 1 divided by the resistance of this resistor. As we know from rearranging Ohm's law, resistance is voltage divided by current. The gradient of this graph is current divided by voltage, the reciprocal of that. So the gradient of this graph is 1 divided by the resistance. The gradient is constant, which means the resistance is also constant. Component number 2, the filament lamp. We need the same circuit, but we're going to swap out the ohmic resistor for the filament lamp. We now want to use the same circuit to measure the current through and the voltage across the filament lamp, so it goes in the same place as the resistor was. Doing the same thing, varying the current and measuring the voltage, we should end up with a table of current and voltage. We can then plot another IV graph. Current on the Y, voltage on the X. The shape this time looks a bit different. It looks a little bit like an S shape, but be careful, it doesn't curve over at the edges. This is showing us something different. Now, current and voltage are not proportional for the whole graph. There is a bit in the middle where current and voltage are proportional because there is a straight line through the origin in the middle of the graph. But as we increase the voltage through the filament lamp, now the graph is starting to curve over. As we know, the gradient of the graph is 1 divided by the resistance. That means if the graph is becoming less steep, the gradient is decreasing, the resistance is increasing. The resistance will continue to increase until we get that plateau at the top of that graph. Now here's the physics behind why that happens. The more current that goes through that filament lamp, the hotter it gets. We know that current leads to heating effect. In fact, we can work out the power wasted due to heating using the formula P equals I squared R, or power equals current squared times resistance. So more current means more heating. The hotter that filament lamp gets, the faster the particles in that filament lamp move. All of the metal ions in that filament are going to be vibrating much faster because of the higher temperature. The fact that they're vibrating faster means that electrons that are flowing through that wire are going to collide with those ions far more often. It's going to make it more difficult for the electrons to flow through that wire. That means the wire's resistance increases. And if resistance increases, current decreases. So as we can see, if we try to increase the current further, we increase the heating effect, we increase the temperature, we increase the resistance, and we decrease the current. The changes we make to try to increase the current just end up decreasing the current again. And that's why we have that maximum current value in the positive and negative parts of the graph. That gives the filament lamp its characteristic IV graph. That's 2 out of 3 done. The third component is the diode. Quite different to the other ones. Unlike an ohmic resistor or a filament lamp, which is just pieces of metal, a diode is an engineered piece of equipment built specifically to do its job. A diode is designed to only let current flow one way around a circuit. To do that, it has to have low resistance in one direction, but really high resistance in the other direction. It's quite difficult to engineer that. They're made of materials that we call semiconductors that only conduct in certain conditions. The circuit we need is also slightly different. We need quite a low current to let this diode operate properly. So we're going to add in a second resistor in addition to our variable resistor to bring that current down a little bit more. Because the current will be so low, we're going to change the ammeter for a milliammeter. It'll measure milliamps or thousandths of an amp. And we'll swap out the component that we need. Let's change the filament lamp from the previous circuit to the diode for this final one. Now we have a circuit we can use to measure the current through and the voltage across the diode. Same thing as before, we're going to vary the current and measure the voltage. The diode has two directions: forward bias and reverse bias. If it's connected in forward bias, it's allowing current to flow the way it's designed to let it flow. If it's connected in reverse bias, it's going to block current flow because it isn't connected in the way it's intended. This time we're also going to swap the power supply around, changing its polarity to get some negative voltage and current. This will show the diode doing its job, not letting current flow in reverse bias. Now we can plot our final IV graph. This graph is unlike the other two. The other two graphs are symmetrical if reflected in the line y equals minus x. In other words, the top right and bottom left quadrants of the graphs show us the same idea. This one's quite a bit different. The negative x-axis is our reverse bias side of the graph. This shows very little current flow on this side of the graph. In fact, at GCSE, we might say there's no current flowing here. We might just ignore it. In reality, there will be a very, very small negative current. Because the diode isn't 100% effective at its job, it will let a little bit of current trickle through. We call this leakage current. So there'll be a very, very small negative current in the reverse bias side of the graph. On the forward bias side of the graph, the positive x-axis, we're also going to get a little bit of current flow up until a certain voltage is reached. We call this threshold voltage. And beyond this threshold voltage, we get a very rapid increase in current and a very high current flows. This is when the diode is allowing the current to flow freely in the direction it's intended. It's the engineering of the diode, the extremely high resistance in reverse bias and low resistance once threshold voltage is reached in forward bias, that gives it this characteristic IV graph. So there we have it, our three IV characteristic graphs. The ohmic conductor has a straight line graph, the filament lamp has its S-shaped IV graph, and the diode has its unsymmetrical IV graph. We now know the circuits required to take the data to draw these graphs and why those components have those graphs in the first place. We do go slightly more in depth at A-level with these components and some thermistors, but we'll leave that for another video. I hope you've enjoyed the video. Please leave a like and subscribe if you want to see more informal physics content like this. Also, please comment below if there's an area of physics you'd like me to cover in a future video. Thank you very much for watching. I'm Howard, and that is how it works. Oh, I'm gonna sneeze. I need to look in the camera. Oh, I need to sneeze. The other two graphs are symmetrical in the line y equals minus x.